Hey, I'm Dave, and I made this crazy robot, Crackjack. It has no wheels. Let me tell you what I learned during its build. I was inspired by Droopy, a 3-pound bot in NHRL. It's a gyro walker, and that means it uses its weapon and its gyroscopic effects to effectively move. NHRL rules give a bonus to such non-traditional movement type robots. And Spark also gives an even bigger bonus in the 1-pound class, 100%, as long as the movement doesn't use wheels or cams. I couldn't make out Droopy's weapon assembly, so I got to work, designed my own, and started to work a prototype.
A little bit about how this robot's going to walk. The weapons are going to be counter-rotating, and when I want it to walk, I am going to speed up one side and make it rotate faster, and I'm going to slow down the other side at the same time. Because of the gyro effect, that's going to have the net effect of pushing down on the slowing weapon and lifting up on the faster weapon. And so that effectively is going to lift the one side of the bot up. At the same time, there will be a braking factor going on with that other weapon, and as a result, it's going to create a net torque that's going to rotate the entire robot around the foot, the left foot in this case. Then to make the next step, I reverse the process.
Finally, I got a working prototype here, and I posted it to social media to see what other people thought. Specifically, I was concerned about whether or not I would get the full weight bonus that I interpreted from the Spark rules, an additional pound in the 1-pound class for a non-wheeled, non-shuffler robot. It was clear that there were a lot of different perspectives on the thought, and pretty much most people tended to think that it was only up for the 50% like a shuffler. Important to know that the event organizer always gets full discretion on how much bonus they'll apply for a given type of robot movement. So make sure you check with your event first. I was not going to be able to get the full 1-pound bonus that I thought I would be able to get with this design. And in fact, the particular event I was going to, the host confirmed that I would only be getting a 50% bonus. So now I had to go back and redesign the bot to fit within a 1.5-pound package instead of a 2-pound.
So a lot of the geometry is interrelated. Since I want to optimize the weight, I need to make this as compact as possible. To maximize the affected area, the weapons, they need to be as close together as possible. But to have a big enough impact, the motors need to be large. I have to fit all the equipment in the middle, and I need to get the weapon blade getting as close to the ground as possible, or at least close enough to be able to hit most robots. I do have kind of a zone that is not able to hit any robots, and I want to try to minimize that. I ended up selecting a 15-degree angle, which gave me the best amount of ability to hit low on the robots, but still maintain the ability to not rub the rotors against the floor. To enable walking when I'm upside down, I put basically a little mohawk feature in the center of the bot. The weapon does not touch the centerpiece. It is wide, so it can support then to prevent rotation in that direction. And then additionally, I extended the axles of the weapon and put little rubber feet on those axles so that everything was kind of in line. So when upside down, none of the weapons are touching, and it's more or less stable. However, I found that this doesn't walk as well because the amount of traction that you get on these little rubber feet aren't very good. Okay, the equation for how much force is going to be coming and lifting up on the bot during its step is going to be related to the moment of inertia of the weapon times the angular velocity of the weapon times the change in angular velocity of the weapon. So these are all somewhat linear, with the exception of the inertia, which is actually mass times the radius of the gyration squared. So if I can put more weight on the outside, this becomes a nonlinear way of improving the stepping. Or affecting the kV of the motor would also potentially increase the force, the base speed at which it's operating. Or if I change the gearing from the motor to the weapon, that could also increase the angular velocity. And then finally, what will affect the change in angular velocity over time? I can do either a faster change, and do it more quickly, or I can change the increase that is possible of the angular velocity. So any of that then could be affected by, let's say, the ESC amperage, or just in general the ability of the angular velocity to change. Or again, maybe how I do the settings on the transmitter. For robot control, I want to be able to start all the weapons, both weapons at the same time, and then depending on which way I want to walk, I want to be able to add and subtract speed to whichever side I want to pick up. Setting up the transmitter to operate this way is relatively straightforward. In a typical mixing setup for a regular robot, you'd mix to switch both channels onto one stick, so that moving in one direction transmits to two channels. Basically, we want to do the same exact thing for this gyro walker, except we want to move one channel to the throttle and maintain the left and right on the opposite stick. So basically at this point, I change out the elevator stick for throttle, and all the other settings are the same. I do make one other change, and that is to limit the aileron to about 62% of the total possible range, so that I don't totally stall out the motors when I try to move left and right. To make the weight limit to 1.5 pounds, I had to initially go down from this 3/16 thickness blade to a thinner 1/8 inch piece. I didn't like the performance as much, so I went to a design piece that had less weight but had more weight towards the outside for the moment of gyration, the higher inertia, and keeping a thicker 3/16 inch blade.
To also save weight, I thought about changing up the motors from the current 3530s to something smaller like a 2822. I did not have 2822s handy, and I realized that I would probably need to really optimize and change the robot quite a bit to take advantage of those much smaller motors. With only a few days left to the competition and trying to make the weight changes, I opted not to change out the motors. The final configuration I ended up with was the 3530s with a 35 amp ESC tied to a 650 milliamp hour battery with about 60 C discharge rate. I did try to go with smaller batteries, but the 30 C to 45 burst rate batteries that I had at the smaller 300 mAh did not do the job. I was not able to get the gyroscopic precession to allow me to walk. Just not enough amperage, I think, to really run it. So I would have to then either reduce the weapon size, like you saw from the equation, or play with something else to enable enough force to lift up the bot for walking. Well, now that I had gotten the bot all put back together and was meeting weight, it was time to take it to the competition. I had 2 fights. I'll show you how they went and summarize after.
All right, we're going to start this fight in 3, 2, 1. Fight, robots, fight. Crackjack, put the spin up, and there's the spin for this. Is it snake line? Snake skin, sorry. Snake skin trying to find a good angle of attack. A little difficult with Crackjack's coverage there. Crackjack moving over a little slowly, but he's getting the job done. The robots being in the middle there. Well, they're really engaging, but not quite getting the fights they need to do damage. The robots spinning very fast. I'm a little surprised that Snakeskin is struggling to push the robot without wheels. He does have a weight bonus, sure. I can't believe both of these robots have fully functioning weapons. That's the first hit there. Beautiful shot there. Might have knocked out one of those weapons on Crackjack. That's bad, as those weapons have also this method of locomotion. Oh, that's not looking good. Crackjack, if I don't see movement, I'm going to have to count you out. Yeah, well, let's pull it.
All right, let's get this match underway in 3, 2, 1. Fight, robots, fight! Let's see Crackjack. He's in there. Whoa! Walking like this to get across the arena. Uh-oh, head goes to the hammer. Hammer, oh! Now he's upside down. Oh! Get over there. Biscuit. Oh, and break the hit. Crackjack. Spinning those buttons up, trying to get a long curve there. Both robots were spinning up full speed. Crackjack able to move. Biscuit still engaging. All right, I'm going to start counting out, Crackjack. I'll count you down. 10, 9, 8. Oh, we got to tap out. He tapped out. He said, I don't want to get pushed into the hammer. That 100-pound pulverizer is very destructive.
So I was successful in starting to walk at the beginning of the match in both matches. I lost them both, unfortunately, because I ended up not being able to keep the motors rotating the weapons. The main reason, the TPU interface that I had with the aluminum driving gear was too rough on the TPU. You can see it basically wore away on the TPU. And because of that, I ended up losing any traction to get the motor spinning after a couple hits. So I'm going to have to take a look. These were Mod 1 based gears that I made. My first guess is to try out a larger, maybe 1.5 mod gear setup. And I'm hoping that the teeth with a better overlap in the mesh will prevent shearing and enable me to continue operating for longer in a fight. Well, that was what I learned from making Crackjack. I hope you enjoyed what you're watching. If you've got some thoughts or some ideas I should try, glad to hear it. Please let me know in the comments.